Hi everyone. Today we're going to talk about Chapter 1. In particular, we'll discuss matter, and later on we'll discuss measurements and calculations in chemistry. So first, let's define matter and mass. Matter is anything that has mass and occupies space. Mass is a measurement of the amount of matter in an object. So on the right, you can see a picture of a table with some food, some silverware, some napkins. Everything in that picture is matter, and all of that matter has mass. Now, mass is independent of the location of an object. So an object on Earth would have the same mass as it would on the moon, for instance. Now, in contrast, we have weight, which is a measurement of the gravitational force acting on an object. And weight does depend on the location of an object. So, for instance, if we have a person on Earth with a mass of 50 kilograms and a weight of 110 pounds, and then let's say that person goes to Mars, they would have the same mass on Mars of 50 kilograms, and their weight would be different because Mars has a different gravitational force. So their weight on Mars would be much less. It would be 42 pounds. Another example is if we have an object that weighs 1 pound on Earth, it would weigh about 0.17 pounds on the moon. And that's because the moon has a different gravitational force from Earth. Now, we perform all of our chemical reactions and measurements here on Earth. So we use something called a balance to determine the mass or the weight of an object. And you might find that I use the terms mass and weight interchangeably. All right, now there are different ways that we can describe matter, and we're going to start by looking at physical and chemical properties of matter. So physical properties can be observed or measured without attempting to change the composition of the matter being observed. So let's start by looking at these gummy bears on the left, and let's focus on the one on the top here. So that gummy bear is blue, it's in the shape of a bear, and it has a particular mass. So those are all things we can use to describe that piece of matter. Now, additionally, let's look at the example in the middle here. We have boiling water, and water boils at 100 degrees Celsius. So that is what we call its boiling point. And water, when it boils, doesn't become something new. It's still water. It's just going from a liquid into a gas state. So boiling points are also physical properties. So again, physical properties are descriptions of objects or matter that we can use without changing the composition of matter. On the right, we have two different metal chains here, and you'll notice the chain on the right is gray, and the chain on the left is a bit red and has some rust on the surface. So we would use the color to describe the differences between those two chains. Now you can also think of physical properties in terms of humans. For instance, I have blue eyes, and that's a physical property that will not change. I also have brown hair, and the only way to change the color of my hair is to perform a chemical reaction. So that would be another physical property. Now, chemical properties, on the other hand, can be observed or measured only by attempting to change the matter into new substances. So one example is flammability. So if something is flammable, then that means that is a chemical property of that matter. If something has an ability to react, that's also a chemical property. So for example, when vinegar and baking soda are mixed, they end up producing this fizz. So we get a lot of gas being produced there, and that tells us that vinegar and baking soda do react together, and therefore that would be their chemical property. Another way we can describe matter is with physical and chemical changes. So physical changes take place without a change in composition. And earlier we saw the example of boiling water. So water was not changing its composition, it was just going from a liquid state to a gas state. So other examples of physical changes would be freezing or melting. But additionally, we can also change the shape of an object without changing its composition. So for example, if we chop wood into kindling, we're not changing the wood itself, we're just changing its shape. So that would be another physical change. Now, a chemical change will be accompanied by a change in composition. So for instance, if we were to burn paper, we are changing the chemical composition of that paper. So we're producing smoke, we're producing ash, etc. And then we also saw on the last slide that when vinegar and baking soda are mixed, they form a type of gas and they end up fizzing, and that is also a chemical change. Additionally, we saw the example of these chains where the chain on the right is nice and gray and the chain on the left has some rust on it. The process of rusting is a chemical change. So most likely the chain on the left did look like the chain on the right at one point in time, but due to reactions with moisture in the air and oxygen in the air, that chain ended up forming some rust on the surface. So we took something that was likely a pure metal and changed it into a new substance, rust. Now, all matter is made up of tiny particles called atoms, and Dalton's atomic theory from 1808 describes atoms. And since 1808, we've come a very long way, and we have determined that everything is made up of these atoms. And in fact, substances called elements are made up of atoms that are all identical. So, for instance, we breathe oxygen, and if we could zoom in on oxygen gas, we would find that there are molecules of oxygen. So you'll notice these little molecules of oxygen floating around. And those are actually elements because they're only made up of oxygen atoms. Up above, we also have a depiction of an atom of oxygen. And we'll talk more about this type of picture later. But there are also substances called compounds. And compounds are combinations of atoms of two or more elements. So that's really key. So elements are made up of one type of atom, whereas compounds are made up of two or more types of atoms. So for instance, carbon dioxide is the gas that we breathe out, and carbon dioxide is made up of one carbon atom and 2 oxygen atoms. Carbon monoxide is another type of gas, and this is actually poisonous if we inhale too much of it. It can replace oxygen in our system, and that's why you should always have a carbon monoxide detector in your home. So carbon monoxide is made up of 1 carbon and 1 oxygen. So carbon dioxide and carbon monoxide are compounds because they have 2 or more different elements, whereas oxygen is just an element because there's only one type of atom present. Now, every molecule of a specific compound will contain the same number of atoms of each kind of element found in the compound. So, for instance, let's go on the last slide here. We already said that carbon monoxide molecules or compounds contain 1 carbon and 1 oxygen. And that is always true for carbon monoxide. That never changes. Unless we, of course, perform a chemical reaction. And we'll talk more about that later. Carbon dioxide, we said, always contains 1 carbon and 2 oxygens per molecule. Another example is this water molecule, which we call H2O. And water, we can see, always contains 1 oxygen and 2 hydrogens. And that never changes. So we'll have the same ratio of atoms per molecule. Now, in chemical reactions, atoms can rearrange, they can separate, or they can combine, but they are never going to randomly disappear, or new atoms are never going to randomly appear. So in chemical reactions, atoms are never created nor destroyed. So as an example, on the right-hand side here, you can see we have 2 purple atoms. And we're going to react those with this red molecule. So this is our molecule. You can see that the 2 atoms are combined there. And that molecule contains 2 red atoms. Now the arrow here is going to indicate that we're performing the reaction, and then on the right-hand side of that arrow we have our products. And you'll notice that we have 2 molecules. And each molecule contains 1 red atom and 1 purple atom. So if we were to add up the different types of atoms we have on the left side of the arrow and the right side of the arrow, we would find that we have the same number of atoms and the same types of atoms on the left and the right. So we didn't lose any red atoms, we didn't lose any purple atoms. They just rearranged to form new molecules or new substances. So this is according to the law of the conservation of mass. So we're not going to, again, lose any atoms or gain any atoms randomly. We'll always have the same number of atoms on each side of that arrow. Okay, so I've been talking about these molecules, and let's define what a molecule actually is. So a molecule is the smallest particle of a pure substance that is capable of a stable, independent existence. So for instance, if we had a glass of water we know that water has 1 oxygen and 2 hydrogens. So it's H2O. So this would be a single molecule of water. And this molecule of water has a stable existence, and it also has the same properties as a bulk amount of water. Now, atoms are what make up those molecules, so we already talked about how we have 2 hydrogen atoms and 1 oxygen atom within water. But let's look at some other examples. So let's say that we have some copper piping. If we were able to zoom in on this copper pipe, we would find individual copper atoms all arranged together. Now, what if we had some sugar? And let's say we were adding it to our coffee or to our tea. If we could zoom in on those sugar molecules, so for instance, we've got 1 sugar molecule there. That molecule has a lot of different atoms making up that structure. And the last example is oil and water. Now, oil and water do not mix. And you can see down below, if we were able to zoom in on that barrier between oil and water, water is on the bottom. And again, each molecule of water has 2 hydrogens and 1 oxygen. And then if we could zoom in on an oil molecule, we can see that there are a bunch of atoms that make up 1 single molecule of oil. Now, there are different ways to classify molecules. So, for instance, we can have diatomic molecules, which contain just 2 atoms. And some examples are oxygen and nitrogen. So, oxygen and nitrogen are both present in air. And in fact, air mostly consists of nitrogen, and oxygen comes in second. But nitrogen and oxygen like to exist in pairs. So you can see here we've got a pair of nitrogen atoms that are forming a diatomic molecule, and we also have a pair of oxygen atoms that are forming a diatomic molecule. There are other examples, so carbon monoxide, which we saw earlier. Carbon monoxide has a carbon atom and an oxygen atom, and that would also be considered a diatomic molecule because we have 2 atoms. But in the case of carbon monoxide, those 2 atoms are different. We also can define molecules as triatomic if they contain 3 atoms. So earlier we saw the example, of carbon dioxide. And we said that carbon dioxide has 1 carbon atom and 2 oxygen atoms. So that's a total of 3 atoms. And then finally, if we have more than 3 atoms, we would call that molecule a polyatomic molecule. So sugar, for example, has many different atoms. We have some carbon atoms, which are shown in black. We have oxygen atoms, which are shown in red. And we have hydrogen atoms, which are shown in gray. Now, another way we can classify molecules is by referring to them as either homoatomic or heteroatomic. So homoatomic molecules contain the same type of atom. And we saw the example of nitrogen and of oxygen. And both of those molecules have the same type of atom present, so they are homoatomic. Heteroatomic molecules, on the other hand, have 2 or more kinds of atoms, and the example we saw earlier was carbon dioxide, or CO2, and this has a carbon atom in the middle, and then 2 oxygen atoms, one on either side of the carbon. So because we have 2 different kinds of atoms, this is a heteroatomic molecule. Now let's go over a quick example. In this example, we're going to classify the molecules as either diatomic, triatomic, or polyatomic. So on the left, we have 4 different molecules, or I guess they're the same molecule, but we have 4 molecules total. So let's kind of focus on one molecule. This molecule has 2 hydrogens, shown in white, and 2 oxygens, shown in red. And then down below, we have what's called the chemical formula for this molecule, which is H2O2. So we have 2 hydrogens and 2 oxygens. And this is actually the chemical formula for hydrogen peroxide, which you might use at home for cuts and scrapes. It can also be used as a bleaching agent. And then on the left-hand side, we have 2 different types of molecules. We have a water molecule here, and then we also have oxygen molecules. So I'm going to let you pause the video and try to determine if these molecules are diatomic, triatomic, or polyatomic. And when you're ready, you can restart the video and see if you got the right answer. Okay, so let's go over the answers for these different molecules. So on the left, H2O2, or hydrogen peroxide molecules, contain 2 different types of atoms. But additionally, we have 4 total atoms within each molecule. So we have 2 hydrogens and 2 oxygens. This means that H2O2 is a polyatomic molecule because we have more than 3 atoms total. On the right-hand side, if we focus on water, water has 1 oxygen and 2 hydrogens for a total of 3 atoms, so it is triatomic. And then oxygen has 2 oxygen atoms, and those 2 oxygen atoms mean that we have a diatomic molecule. Now let's classify these same molecules, but this time we'll use the terms homoatomic or heteroatomic. So again, we're focusing on hydrogen peroxide, water, and oxygen. And if you would like to pause the video and try this on your own, you can, and then you can restart the video when you're ready. Okay, so let's try to determine whether these molecules are homoatomic or heteroatomic. So H2O2 has 2 different types of atoms, as we said before, so that would be classified as heteroatomic. So we've got 2 different types of atoms there. H2O also has 2 different types of atoms, hydrogen and oxygen, so that would also be considered heteroatomic. And then finally, oxygen contains 2 of the same kind of atom, so that would be homoatomic because it has the same 2 atoms there. All right, so let's summarize what we learned about how to classify molecules. So to start, we said that we can use either the terms diatomic, which means that it contains 2 atoms. And those atoms can be different or the same. So for instance, we saw the examples of oxygen and nitrogen and carbon monoxide. There's also the term triatomic, which means that a molecule contains 3 atoms. And we saw the example of carbon dioxide. And then we have the term polyatomic, which contains more than 3 atoms. In addition to that, we saw the term homoatomic, which means that a molecule contains the same type of atoms. And we saw the term heteroatomic, which means that a molecule consists of more than one type of atom. And I apologize, my pen is freaking out here, apparently. All right, so these are the key words to know, and I recommend making flashcards if that helps you to remember these different terms. I also recommend reading through this section of Chapter 1 so that you can reinforce some of these concepts. And then I will also post some other resources on Canvas under modules so that you can see maybe some other descriptions of this material. But I will see you in the next video where we will talk about another way to classify matter.